Welcome back. Let me tell you a bit more about inverse functions. We're going to give a more explicit definition in this video. But before we do that, let's just recall what we learned in the last video. So when we were asking, what is f inverse of some number, call it y, we're asking the same thing as what value of x makes f of x equal y. They're the same question. So the definition that we gave last time was if f of x equals y, then f inverse of y equals x, because that's the x value that gives us an output of y. So let's try to interpret this definition graphically. F inverse of 3 is the value for x that I plug in to get an output of 3. So if my output is 3, my y value is 3, my input was 2. So f inverse of 3 is 2. F inverse of 6, I go to the y value being 6, and I figure out what the input was to give me that. So f inverse of 6 is 5. So here's a question. Let's see if you remember composition of functions. What if I compose the function f with the function f inverse? Interesting. So f inverse of 3 is 2. We just figured that out. So what I'm looking for is what is f of 2? F of 2 is the output. When I plug in 2, I get 3. Curious. F of f inverse of 3 is 3. Let's see if this is true for another example. So what if we do f of f inverse of 6? F inverse of 6 is 5, because when I have an output of 6, my input is 5. I'm doing f of 5, that's 6. Can you see a pattern? If I give you an output, you figure out what the input is that was associated to it. That tells you f inverse of that number. You plug that input back in, you get back to where you started. So when you actually have an inverse, it's always true that when you compose the two functions together and evaluate, you get the thing you plugged in. Let's write that down. So f and f inverse are inverse functions. Let's get rid of this. Functions if and only if, when I compose them, so if I do f inverse of f of x, I get x, and if I compose them in the other direction, f of f inverse of x, I also get x. So let's see why this is true from our old definition. So f of x is going to be some value of y, some value y. So I'll be looking at f inverse of y. But from our old definition, f inverse of y is x when f of x equals y. So that's just x again. In the other direction, if I do f inverse of x, that's going to be, so f inverse of, well, this is just a placeholder, so we can think of it as f inverse of y. So if I do f inverse of some y, let's change these to y's too, just so we're consistent. F inverse of some value y is going to equal x if, when we plug x into f, we get y out. So f of x has to be y. So these two compositions will always give me the thing that I plugged in. This is the true definition of inverse functions. Compose them, get out what you started with. Okay, so let's see an example of that. So this example we saw in the last video. We computed that f inverse of x just ended up being the cubed root of x plus 2. Remember, we computed this by saying, when does f of x equal triangle? We'll set f of x equal to triangle and solve for x. That's how we found it. So it's the cube root of triangle plus 2. Now I'm just using the variable x instead of triangle. That's all. So now if we try to compose these, f of f inverse of x should equal x. But let's do it. So I'm doing f of the cubed root of x plus 2. And f is x cubed minus 2, so I plug this whole thing in for x. Get cubed root of x plus 2 cubed minus 2. Now if I cube a cube root, those things undo each other. So this is just x plus 2 minus 2, which is x. If I compose in the other direction, if I do f inverse of f of x, then I'm shoving the f function in for x into f inverse. So I have f inverse of x cubed minus 2, which is just the cubed root of x cubed minus 2 plus 2, which is the cube root of x cubed. Cube root undoes x cubed, so I'm just left with x again. This is a really important example. This basically says that cube root is the inverse of cubing. So taking the cubed root goes in one direction. So you have maybe triangle, cube root, and triangle cubed. These are opposite operations. Because when you compose them, you get triangle out. That's what makes them inverse functions. One more example using the chart that we saw in the last video. If I do f of f inverse of 2. So remember, f inverse of 2 was the value of x that we plugged in to get out 2. We get out 2 when x is negative 1, so we have to do f of negative 1. We went that way to figure out what f inverse of 2 was. But then to do f of negative 1, we go in this direction on the chart. So we just go back. We get 2. F of 2 is the value that I get out when I plug into. So that's 3. F inverse of 3 is the x value I plugged in to get out 3. So I go backwards in this direction, and I end up with 2 again. So whatever I plugged in to the composition of f with f inverse, I get that same thing back out. So these are in fact inverse functions. Okay, so we're going to make things a little bit more complicated in the next couple videos. We're going to learn how to figure out inverse function, the expression for an inverse function, when the original function is much more complicated than the ones we've been looking at. And then we'll look at cases where inverse functions don't necessarily exist. And maybe start to think about why that might happen. Here's a hint. What if we look at the function f of x equals x squared? What undoes the squaring function? Think about that. Also think about if f of x equals 4, say, what is x? So what is f inverse of 4? We'll go back over this example so you can see why it's so interesting. Good luck with the web work.